Okay, finally success. I recorded part of the solutions to those earlier problems and everything worked out good because my previous two attempts did not work out so good. Alright, so let's continue this. Suppose we have a function here, a log function, and they're asking us to determine the domain. Remember that our log functions are the inverse of exponential functions. And whenever you have two functions that are inverses of each other, the domain and range has switched. So if you recall, if we had 3 to the x, we knew immediately that the domain was all real numbers. Okay, and now the range, since there's no transformations that are affecting the y-coordinate, and sometimes the y-coordinate will be different, but for 3 to the x, the range was would be 0 to infinity. So here, if we're looking at log base 3 of x, these two are inverses of each other. So the domain and range has switched. So the range of 0 to infinity is now my domain, and this domain is all real numbers, is the range. So when I had an exponential function, I knew always that the domain was all real numbers. If I have a log function, I know always that the range is going to be all real numbers. Now, the range here and the domain here are going to depend upon transformations. They are not always going to be 0 to infinity. They will be if it's basic, if you haven't moved it up or down or left or right. If there's no transformations, then hey, it's 0 to infinity like we just written. But from function to function, these answers may change, whereas the domain of an exponential function is always all real numbers, and the range of a logarithm is always all real numbers. So I know when I see a logarithm and they're asking me the range, I don't really have to put in all that much thought because I've already thought about it, and the range is all real numbers. Alright, so like we say, we know that this guy is going to be 0 to infinity, but let's look a little bit closer. Let's look at the graphs. The graph of y equals 3 to the x raised to the x power, that 3 is bigger than 1, this is an increasing function. We knew that it crosses through a y-intercept of 0, 1. The inverse function, domain and range, have switched, and the picture of the graph will be a reflection across the line y equals x. Here's a 45-degree line. So this line is serving as a mirror. The image to the left is reflected over here, and if the domain and range have switched, the x and y's have switched, 0, 1 is transformed to 1, 0, and to where the horizontal asymptote for the exponential function now becomes the vertical asymptote for the logarithmic function. So this log function is getting closer and closer to this dashed line at the y-axis and never touching it, and that's the vertical line x equals 0. So if our graph is entirely to the right of that, and if you're going to describe, if you take a look at every point on this graph and you focus on the x-coordinate, one thing all those x's have in common, they are positive numbers. You will never find an x-coordinate that is 0. You will never find an x-coordinate that is negative. So that's for this specific problem. So for this number 3, the domain of this log function is positive real numbers. Hey, it's always going to be the case that if they ask me for the range of any log function, doesn't matter how complicated the expression is, if it's a log function, the range is all real numbers. Alright. The asymptote. Well, we were just talking about that. Again, if we think about this logarithm, where exponential functions had a horizontal asymptote, these log functions will have a vertical asymptote. And we have seen in the past that when we studied rational functions, that vertical lines are x equals, horizontal are y equals. This y-axis is the line x equals 0. So let's be more specific. If they're asking me about the asymptotes of this graph, there is no horizontal asymptote. The vertical asymptote, I don't want to just write 0. Remember, I want an equation is x equals 0. So you can see if you look back at those previous problems, this had switched. When we were looking at exponential functions, it didn't have a vertical asymptote, but it had a horizontal. Well, now that domain and range has switched, the graph has been reflected across the line y equals x, and now these log functions will have a vertical asymptote but no horizontal asymptote. Alright. The x-intercept. Doesn't matter what kind of function it is, whether it's exponential, logarithmic, whether it's quadratic function, doesn't matter. To find the x-intercept, you let y equal 0. So we know that when we started learning about function, they renamed the y variable. They started calling it f to think in terms of input and output. But we can go back old school and call that f y. So if I have this equation that y is equal to log base 3 of x, to find the x-intercept, we let y equal 0. Okay, so now that's no problem at all, because remember that the range of the logarithmic function was all real numbers, so the output of this could be 0. But it's going to be difficult for me to solve this equation and stuff. I'm going to rewrite this. I'm going to use my definition of logarithms. I know that this 3 is referred to as the base, and I know this base is going to have this number is going to have an exponent associated with it, and the definition of these logarithms is such that the logarithm equals the exponent. So this base of 3 has an exponent of 0, and that's equal to this argument of x. Okay, by definition, my laws of exponents, sometimes they'll call them laws of exponents or properties of exponents. By definition, 3 to the 0 is equal to 1. So this graph is crossing the x-axis at 1, or if you're plotting the point and you plot it, you put a dot at 1, 0. So if we sketch the graph, we just got done saying that there is a vertical asymptote at x equals 0. Your graph gets closer and closer and closer to that, but never touches it. Comes up and it intersects the x-axis, and then it keeps going like this, and the coordinates of that point is 1, 0. Alright. The y-intercept, doesn't matter what type of a function it is. If you're trying to find the y-intercept, you let x equal 0. And remember, for a moment, we can think about, rather than letting the function notation confuse us at all, instead of writing f, we can think of that as y. That's how we first learned it. So if x is equal to 0, we have y is equal to log base 3 of 0. Well, we've got a problem there. The domain of the logarithm had values of x that were bigger than 0. Go back and look at that. Bigger than 0. Okay, so you can't take the log of 0. Okay, so this guy's undefined. We can't. There is no y-intercept. And if you think about what that graph looks like, there was a vertical asymptote, and your graph never touches that vertical asymptote. And that vertical asymptote, that line x equals 0, was the y-axis. So it's never crossing the y-axis. There is no y-intercept. So let's move on. Now we have a different logarithmic function, and I would rewrite this. I like to have the x coordinate first, so 4 minus x can be rewritten as negative x plus 4. Alright, so what kind of transformations are going on here? Well, the plus 4 is bizarre. It's to the left 4 units. The negative sign is a reflection, and you have to determine what is it a reflection across the x-axis or the y-axis. If you're taking the opposite of x, what was to the right is now to the left. You're reflecting across the y-axis. And this minus 3 on the outside of this parenthesis, you're going down 3. Okay, so the domain is a set of x values, and x controls left and right. This down 3 is affecting the y coordinate, up and down. This down 3 is not going to have any effect on me determining the domain. But these two transformations are. I need to originally think about what the parent transformation, about what the parent function is. I need to first just think about the graph of ln of x. And then I need to perform these two transformations. So let's shrink this up and give ourselves a little bit of work here, a little bit of area to work in. Alright. So the graph of this natural log of x, remember this is just log base e, looks like this. Okay, it has an x-intercept of 1. It has a vertical asymptote of x equals 0, like that. Now, if you're going to move this to the left 4 units, if you're going to shift this entire graph to the left 4 units, you also have to shift this vertical asymptote to the left 4 units. So let's make a sketch right here. If this has moved to the left, it's no longer on the y-axis, it's over here. And so 0 to the left is minus 0 minus 4. This vertical asymptote is negative 4. And this whole graph has shifted over to the left. It moved to the left. Okay, and this x-intercept also moved to the left 4 units. 1 minus 4 is a negative 3. Alright, so that takes care of this transformation. But now we have a reflection to think about across the y-axis. So if you have a reflection across the y-axis, what was over here, you're changing the sign of the x's. So if this x is negative 4, if we change the sign of it, it's going to become x equals positive 4. This vertical asymptote got reflected across the y-axis, and it's now over here on the right side at x equals 4. Now this graph also spun around. It's going to have that same y-intercept there, but this negative 3 is going to come over here, and it's going to be a positive 3, and my graph is going to look like this. Okay, so for the set of x's, if I look at all of these points, they're on this graph. If I try to describe the x coordinate, I can see that they're all of these points are to the left of 4, and to the left of 4 is smaller than 4. So no matter how, if you come at it from the right, from negative infinity, all of a sudden these x's are going to be increasing until you get to 4, and there's not a single point that's equal to 4 or bigger than 4. So our domain is the set of all real numbers that are strictly smaller than 4. In other words, from negative infinity to positive 4. Alright. What about the range? Hey, the range, I don't have to, there's little thought into what the range of a logarithmic function is. It's always all real numbers. So this range, because remember, it was that this range used to be the domain of the exponential, and we knew that the domain of any exponential function is always all real numbers. Now I know, since this is an inverse function, domain and range have switched. The range of any log function, doesn't matter how many transformations you have, or how complicated they are, the range is all real numbers. All right, the asymptote. Well, we were already talking about that. We thought about that asymptote to help us to determine the domain. We know that we came to a conclusion that the vertical asymptote was x equals 4. So it had no horizontal asymptote. And the vertical asymptote is the line x equals 4. All right. The x-intercept. To find the x-intercept, you let y equal 0. Always. Doesn't matter whether it's a log function, exponential function, quadratic function, any kind of function. All right. For x and y intercept, let's not use function notation. Let's go back to old school. Use x and y's. If I'm trying to find the x-intercept, I'm going to let y equal 0. If y is equal to 0, I haven't moved up or down, and I'm guaranteed to be a point on the x-axis if there is one. So on the left-hand side, we replace the y with 0, and now we solve this equation for x. So the two terms on the right, the term that has my variable is this first term, so I need to add 3 to both sides to isolate the term with my variable. So I have 3 is equal to the natural log of 4 minus x. Now remember, natural log is just log base e, and I even suggest that when students first start learning these logarithms, it's okay to rewrite ln, which just stands for natural logarithm, as log base e. So I need to rewrite this form. I need to have the same equation, but to have it be in exponential form. So the base is e. Now e is like pi. That's e is approximately 2.718. Just like, back in the geometry days, pi was 3.14. It's an irrational number that actually goes on forever with no kind of a repeating pattern. So this base is e. We know a logarithm equals an exponent. This base has some exponent associated with it, and since the log equals the exponent, this is e to the third power. So this is 2.718 raised to the third power. We can use a calculator here in just a minute to determine a decimal approximation for that. So this e to the third is equal to this 4 minus x. Okay. So to solve this equation for x, if you simply add x to both sides and subtract that e to the third, or in other words, if these two terms switch places, you have 4 minus e to the third. If I go to punch that on a calculator, my calculator is back here out of reach. I have 4 minus e to the third power, and to 4 decimal. If I carry this out to several decimal points, it's kind of ridiculous because negative 16.0855. There's no way if I'm plotting this by hand that I can be that accurate. So I'm just going to call the x-intercept negative 16. You're not going to be able to tell the difference if I plot negative 16 versus negative 16.1. Now some students, and I think this is sometimes a smart idea for people, instead of writing x equals negative 16, they give the coordinates of where you are on the x-axis. Alright, so there's the x-intercept for that. For the y-intercept, you let x equal 0. And remember that we're temporarily not using function notation, that we're just saying, hey, go back to old school and use x and y's. So instead of f, we know that's y. So if we plug in, and oftentimes you hear them say that for substitution, to replace this x with a value of 0, we say plug in 0. You have the natural log of 4 minus 0. Well, 4 minus 0 is just 4. When you're punching this in the calculator, keying it in, don't forget to close that parenthesis. These Texas Instrument calculators give you an open parenthesis after you hit the natural log button. You got to remember to close it. Alright, so there is a button on your scientific calculator that is LN. Press that, press 4, hit the parenthesis button, and then -3. When I do that, I get negative 1.6137 if I carry that out to 4 decimals, but hey, I'm going to be lucky if I eyeball this to graph it, if I can plot the point -1.6. My negative 1.6 is probably going to look a lot like my negative 1.5, right? It's very hard by hand to be more accurate than that. And like I say, sometimes students prefer to write the coordinates. If you're on the y-axis, you haven't moved left or right, x is 0, and you have the coordinates of that y-intercept. Alright. Now we're going to look at that matching. So I think I'm going to stop the video again, so that I don't have any problems with the size, and do this last part, this matching, on a different video. So I do hope this is helping, and I'll talk to you later.